Hey AP friends, today we're going to learn section 3.5, which is a very different type of differentiation we call implicit. What you guys have been doing before up until now is something that's called explicit differentiation, but you didn't realize you were even doing that. You were taking a function that looks something like this, where it was solved for y on each side, and you took the derivative. And the derivative of the left side was just y prime, or dy dx. Or if it was f of x, it was f prime of x. But that was because y was always on the left side of the equation. These were functions. And so we took the derivative, what we call it, explicitly. But not all graphs in math look like that. What if we need to take the derivative of these two friends here on the bottom? Do you notice how these are different? Do you notice how the y is not isolated? How it is buried over here as well, and over here. It's buried inside the equation. These are not functions, but they're still really important for math and for calculus because we can apply them to real life and we need to find derivatives of them as well. Look how beautiful these graphs are. The left one, hopefully you recognize that's a normal circle with a radius of 5. But look how pretty the one on the right is. Really, really nice. But we can still find derivatives. Because if you think about it, on the right-hand graph, I can still find equations of tangent lines and find all these tangent slopes everywhere. It's still possible. So we still need to know how to find the derivative of this. Now, one way we could try to do it is we could try to solve for y, but that might be really hard algebraically. But then the derivative would be really easy. But again, algebraically to solve for y would be really hard. So we need to find a way to just go left to right with brute force and take the derivative of every piece. But when we get to a term that has a y in it, we have to do something very, very special to it. All right? This is going to be implicit differentiation. So here we go. As you see in those last two examples, because the y was buried inside the equation, it wasn't just solved on the left-hand side like we'd normally been doing explicitly, it's buried inside there. We need to find a way to take the derivative of that y term, but we're going to have to use the chain rule. So anytime you touch the y term, any term with a y in it, you have to include by chain a y prime or a dy dx. Let me show you how. So for example, here's number 1. Here's our circle, right, with the radius of 5. I want you to find dy dx, meaning can you find the derivative, or y prime. Now what you have to do is, as you work left to right, you're going to take the derivative as normal with respect to x. So everything is going to be d something dx. So let's take the derivative of just the first term. That's x squared. Okay, well the derivative of x squared is just 2x, right? But if we want to be really, really specific, this would be 2x times, by chain, the derivative of the x variable with respect to x, dx over dx. Now that's going to simplify really nicely, right? But let's just keep going forward for now. Plus, now when we take the derivative of y squared, we're going to do it the same way. Treat the y as if it's an x. And just think, okay, if this was x squared, what would the derivative be? It would be 2x. But since it's a y squared, let's just say the derivative would be, again, by power rule, 2y. But because this is a y variable, we need to include by chain the derivative of the actual y variable, because y is an important letter here. It's not solved for y, so we have to do what's called implicit differentiation. And it happens pretty much right there, where if you took the derivative of a y term over here, you have to include a dy dx in the derivative. Let's keep going. Again, left to right. I got that term. I got that term. This is equal to, let's say, the derivative of 25. Remember, the derivative of a constant is just 0, right? Okay, now, remember we said that the dx over dx term here just disappears. And if that's going to happen every time, do we need to include it? Actually, no, you don't have to. So going forward, if we were to do this one all over again, I'd probably just say the derivative of this equation would be 2x, by power rule, plus yada, 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 and go forward. And I would not include the dx over dx. It is important, and it is there, but we don't have to include it because the derivative of x with respect to itself is always just the number 1. So you don't have to worry about that. It's only when you're playing with the y terms that you have to include a dy dx by chain. All right, now let's see what we have here. This becomes 2x plus 2y times, by chain, the derivative of y with respect to x equals 0. It's also important that you included dy dx there because, remember, what's the question asking for? The question was asking for over here. It was asking for dy dx. So now you're going to take your equation here and try to solve it for dy dx. So now it's just algebra. Okay, this term here has a dy dx in it, so why don't we leave this on the left side, and why don't we move this term over to the right side by subtracting. So I should have 2y times dy dx equals, we're going to subtract the 2x, right? And there you go. Now remember, we're trying to solve for dy dx, so why don't we divide both sides by 2y. Those cancel. And I get dy dx equals, well, negative 2x over 2y, which I can reduce. The 2's cancel. And I get negative x over y. And that is my derivative of y, or y prime. Notice how interesting this is. First of all, in the example, in number 1, did you notice that y was buried inside the equation? Do you notice what your derivative has now? It has a y in it. So when we have to find slope moving forward, we're going to have to plug in both x's and y variables. Very interesting. That's your first implicit differentiation example. Good job. So as you work left to right, anytime you come up with a y term, like you saw in the first one, you have to include the dy dx. Okay, I'm going to erase this work for a second and try number 2. I'm going to give you just a minute. You can pause the video and copy down any steps that you need, and then we'll try number 2. Okay, friends, let's try number 2 here. So this one says find y prime, which again is the same thing as dy dx, if, here we go. All right, that was the cool equation that we saw on the previous page, right? Over here on the right-hand side. And we said we can take the derivative because we can find tangent slopes, so we need to know how to take the derivative. So here we go. Notice, again, your eyes should go here. And you notice that because this is buried on the inside, you're going to need implicit, which means anytime you touch a y term, like here, and like here, you're going to need to include a dy dx by chain. Or, since the question is asking for y prime, you can also include y prime instead of dy dx. Just be careful though. Sometimes my y primes look a little bit like y to the 1. So just be careful about your notation if you use y prime. Make it very clear that it is y prime and not y to the 1 power. Okay, shall we do it? Here we go. Let's go left to right. Let's pick a new color. How about purple? Okay, as I work left to right in this equation, I should get the derivative of x cubed is 3x squared. Now he's an x term, so I don't need to include the dx there. I could, it's true, but I don't need it. Only the y terms I need to worry about that. So 3x squared plus the derivative of y cubed, by just power rule, is 3y squared, right? But because he's a y term, remember, implicit differentiation needs chain, so I'm going to multiply by the derivative of y. And here I'll use the y prime notation instead of dy dx. But they mean the same, and you can use either one you want. Okay, the left side is done. Equals, now look what happens on the right side. Do you notice that, first of all, I'm going to put the constant on the outside. Because again, we learned that if you have a constant in a derivative, you can just leave it in the front and incorporate it back in at the end. Look what I have inside that parentheses, folks. Do you notice what rule I'm going to need? This is, believe it or not, because there's 2 variables multiplying, I'm going to need product rule. Did you see that? This is product rule because I have an x variable times a y variable. So I will need to split them up. Here we go. This becomes, the 6 hangs out on the outside. Now the derivative of xy. Why don't we take the derivative of the x, which is 1, but we keep the y. Product rule says plus, let's keep the x, and the derivative of the y is just 1, because the derivative of a variable, x or y, is just 1. But by chain, implicitly, I need to multiply chain rule-wise by y prime. So really, that parentheses is 6y plus xy prime. Okay? Now, the question here is, can you find for me over here on the left side y prime? That's what I was asking for. So now you have some major algebra to do here, friends. Here is your full derivative from here to here, and you need to isolate your y primes. Okay, this is where just basic algebra is really important. Okay, so let's just rewrite it over here down on the left so I can see it better. We have 3x squared plus 3y squared. And now visually, because I'm solving for y prime, I'm going to put it in red so we can visually see that's what I need to get. Equals 6 parentheses y plus x y prime. Okay, your job is to solve for y prime. And this isn't hard, but it just takes a little bit of algebra. So we need all the y prime terms on one side. But before you do that, look at the parentheses on the right side. I need to free that y prime, so I'm going to have to distribute the 6. Okay, there we go. That looks better. Now that y prime on the right side is free, and now I can bring them over to the left side. So anything that has a y prime term, why don't we bring those friends together on the left side? Which means this one will stay here, this friend will subtract to the left side. And anything that's not a y prime term, we're going to keep on the other side. So the 6y will stay here, and I'm going to move the 3x squared over to the right side. Okay, here's what we're going to get. We should have 3y squared y prime minus, we're going to subtract that other term, 6x y prime. Okay, all the y primes are on one side. Let's put all the non-y prime terms to the right side. We had 6y already there, and I'm going to subtract from the left side 3x squared. It's looking pretty good, but I need to get the y prime by itself, so I think the best thing to do is take this left side, and why don't we just factor out the y prime by GCF. So if I factor out the y prime, left over would be 3y squared minus 6x. That's great. So now the y prime term is almost by itself, and the last step I would do would be to divide this left term on both sides. So final answer, y prime, or dy dx, the derivative, is 6y minus 3x squared divided by 3y squared minus 6x. Now I do see there is a 3 everywhere, so I could divide a 3 out of every single term. As long as it's every single term, and if I divided 3 out of everywhere, top and bottom, I should get 2y minus x squared over y squared minus 2x. All right, this is what y prime looks like. Look how complicated it is here, friends. This is implicit differentiation, where because the y's are buried inside the equations when you take the derivative, you'll probably more likely than not have a y in your answer. So again, these are not functions, and that's okay. We still need to find how to take the derivative of that one. Really good job on that one, friends. Before we do number 3, just look and see how pretty these equations are. For example, figure 7 here on the bottom. Oh my gosh, look at that crazy equation. Totally not a function, but really pretty design. But again, we can still take derivatives here. How about figure 8? Now we incorporate some trig. Once you incorporate trig, wow, it's pretty. We can find derivative of that. And number 9 over here as well. So crazy cool. It's beautiful when they're not functions and you can bury the y's inside the equation. You can make some really interesting graphs. But we need to learn how to use implicit differentiation to find derivatives. Are you ready? Here comes number 3. Okay, again, I'm going to erase all my work here so you can see it better. All right, number 3. Here we go. Let's find, again, it says y prime, but you can also think dy dx. Either notation is fine. If, here is your equation. All right, so now notice a lot of things. First of all, you see how the y is buried. And over here, the y is buried, so you definitely need implicit differentiation. You need the ID. A couple things to notice. This one looks complicated because there's some trig in here. So notice first of all that you have x plus y inside the sign. So I'm thinking chain. And I'm seeing on the right-hand side, I'm seeing the y squared and the cosine x multiplied, so I'm thinking product rule. So lots of things going on. Look at the graph here. Look how pretty that is. Very wavy. Very neat. Okay, are you ready? Here we go. Big breath here. Ready? Okay, let's go left to right. In order to the derivative of the left side here, folks, I am going to need the chain rule. So I'm going to let u equal the inner function of x plus y. So that really, this is just going to turn into the sine of u on the left side. Ready? Let's take the derivative of the left side if I just use chain. The derivative of sine of u is cos of u, but because it's chain, remember we have to multiply by the derivative of the inner function. Okay, that looks pretty good. That's the left side. We'll plug that back in just a sec. On the right side, I didn't use product rule. So product rule says, let's take the derivative of the first term. The derivative of y squared over here, guys. The derivative of y squared, because he's a y term, should be, treat him like a variable. He's 2y. But because it's implicit, you need to multiply by the derivative of y itself. Okay, so I'm going to have over here on the left side 2y by power rule times y prime by implicit chain rule. Okay, but I took the derivative of the first one, and we're going to keep the second term. Plus, okay, let's keep the first term and multiply by the derivative of the second term. That's just cos of x. That doesn't need a chain rule. That just needs normal trig derivative. That's the negative sine of x. Okay, in my next sentence, what I'm going to do is I'm going to take the u's and plug them back into here for cos. So, first of all, you notice where all the y primes are. I have a y prime here. And I'm probably going to have a y prime on the left side, and I'll find that in just a sec. All right, let's plug it back in. Cos of, remember u was x plus y, times the derivative of u. Okay, let's have a chat up here, friends. The derivative of u is the derivative of x plus y, which is half easy and half not. Let's see, just working left to right, it should be the derivative of x is just 1, plus the derivative of y is also 1, but times, by differentiation, implicit, chain, is y prime. So I should get 1 plus y prime is my u prime. Okay, that's the left side. Equals 2y times y prime times cos of x plus y squared times the negative sine of x. All right, let me see. Let me see if I can find all of my y primes. Now I have a y prime here, and I have a y prime here. So just like before, we need to get those terms all by themselves on one side of the equation. Okay, let's analyze a little bit here, guys. On the left side, the y prime is really attached to this whole thing. Ugh. So I think it might be better to, just like we did on number 2 with the 6, why don't we take this whole cos term and distribute inside the parentheses so I can free that y prime. On the right side, the y prime is in this term here. So I'm going to try to move him over to the left side as well. This term on the right-hand side doesn't have a y prime, so he's just going to stay put where he is. All right, we got our plan. Here we go. So I said on the left side, I'm going to multiply the cos into the parentheses. So I'm going to get 1 times the cos of x plus y plus y prime times the cos of x plus y. And again, why am I doing that? Because now I can free up the y prime that I had stuck inside the parentheses, so I can solve for him. Okay, left side is done. Equals, well, while I'm at it, why don't I go ahead and move? Since this term had a y prime in it, we said we were going to gather them together. So why don't I just right now move him over to the left side by subtracting him? That'd be minus 2y y prime cos of x equals, the term that I circled in green there should stay just by himself, and that's just him. Okay, let's see our y primes, just double checking. There they are, there they are. Now that I distributed the cos, do you notice over here that this term doesn't have a y prime anymore? So if we don't need him on the left side, why don't we move him over to the right side? Okay, he's going to become now, let me actually follow that green arrow. Let's go over here. We should have now y prime cos of x plus y minus 2y y prime cos of x. Okay, that's the left side. All the y primes are together. Equals, on the right side, I should have the negative y squared sine of x. That was already there. And we said over here we're going to move this term over. Well, it's times 1, so we can just skip that. So it should be minus cos of x plus y. Man, these are complicated, aren't they? Okay, let me just double check again. Here's my y prime. Here's my y prime. Why don't we factor it out? When I factor it out, both terms I should have a cos of x plus y left in there. Minus, if I take the y prime out of the second term, I should get 2y cos of x. And then the right side is the same right side that I had there. So now, do you see, folks, I'm almost done. To get the y prime by itself, why don't we just divide the right side by this big, massive term there? Okay? And here's what should we get. I'll save it over here on the right side up here. Ready? Drum roll. Y prime equals, okay, the right side was negative y squared sine of x minus the cosine of x plus y. Okay, that was the right side, so that becomes my numerator. I'm going to divide by that whole green underline that I had here, since I factored out the y prime. Cos of x plus y minus 2y cosine of x. Just taking a look and seeing, I do have a lot of coses, but notice that the coses are different. Some coses are just cos of x. Some coses are cos of x plus y. So I actually can't combine them or factor them or eliminate or anything at all. Friends, oh my gosh, look how complicated this is. But congratulations if you made it. That is y prime. Boy, implicit is really tough. You notice that the derivatives are not terrible. It's the aftermath. Look at all this algebra. So there's your introduction. That's why we need to learn how to do this kind of differentiation called implicit. Because not always are the functions just y equals. Boy, I miss those now, right? Y equals, you can just take the derivative. But if the y is buried inside, we need to take the derivative using implicit differentiation, which includes the chain rule, which means every y term now needs to include a y prime or a dy dx, which we solve for. In the next video, I'm just going to throw a couple more examples at you that are really, really good. But I'll save that for next time, and you can watch that later. Great job on implicit differentiation. That is section 3.5. See you next time.